Hi, I'm Catherine Pfaff, and I'm a math professor at Queen's University in Kingston, Ontario. And what I'm going to do is I'm going to go through, so there's a whole series of these videos, and really what these came out of was I was realizing that there were a lot of aspects of functions that my students were getting confused about. And so I went back to, when I taught a Transition to Higher Mathematics course as a postdoc at the University of California, Santa Barbara, and I kind of altered notes from there and brought this as kind of a functions boot camp, I would call it, and gave it in evening lectures to a lot of my students. So I've broken this into a whole sequence of videos, and accompanying each video there should be some notes. So they're going to look something like this, they're going to be colorful and so on. And there should also be, for most of them, maybe not all of them, there should also be kind of a pre-quiz with solutions. So if you wanted to just look through the notes or the pre-quiz to see how comfortable you already are with this stuff, then that's, obviously equally fine. But if you wanted to actually kind of listen, I would recommend, so in the first one, I'm going to go through the function definition, and then what images and pre-images and ranges are. And then examples of function terminology. And then depending on your comfort with, so some things that I find a lot of students get confused about. Well, one thing is they actually get confused about what a function actually is. And this comes into well-definedness. So I did kind of a separate video on well-definedness. And then I did another one on injectivity, surjectivity, and bijectivity. I think most students think they know what these are, but then tend to get tripped up if they're actually supposed to prove something about them. It's also extremely common to confuse well-definedness and injectivity. So I try to kind of highlight that. And then there'll be videos on a wide range of other things. Okay, but let's start with functions. So the function definition, right. And then of course I'm making these videos now during this time because we're not lecturing in person at Queen's, and I thought it would be good to have these videos in the future also. So let's start with the function definition. Okay, so we're going to suppose, and I tend to like to color code things, so I also tend to, mathematicians have kind of these language words, which are almost kind of logic words, and I often capitalize them to emphasize that these are really kind of logic words almost, or in many cases are. Okay, so we're going to suppose that these are sets, so we also have a video on sets. Okay, and then so what is it, a function? Okay, so a function, and maybe we are going to, well, we'll see. So a function f from s to t, yeah, we are going to eliminate this line. Okay, so this is going to be a function f from s to t. And the way that I'm going to denote that is it's going to look like, often we write it like this. So you're probably used to seeing functions written like this, but just to emphasize that that's just the notation for this. Okay, so this is just other notation for the same thing. So it's going to be a rule. Assigning to each element of S assigning to each element in S a single element of T. In my notes I underlined only 2 times in my notes, but we're adding one in more now. So a single element of T. And then you'll have notation that you've seen for that, so we usually write that so that we would denote that. F of S. Okay, so that's the element that it goes to. So the picture, and I'm going to kind of put the picture here. And in fact, I'm going to kind of erase, this is what this section is on, but I'm going to erase it to give myself a little more room. Okay. So I'm going to put, so this is going to be, I'm going to start at S, or in S, right? And then I look at, for each element in S, I'm going to go somewhere. And so then over here, I'm going to have T, right? And then this, so my function f goes like this, right? And then it's going to assign for each element s, it's going to assign it to precisely one element in here. And this I'm going to call this t. I just decided to right now. Okay, so there's a little t there. And this is going to equal, so our notation for this is f of s. Right, this is our output for S. Okay, so for each element of S, I have to get an element of T. It has to be a single element of T, right? So for each element of S, I get as an output an element that has to be in T, and it has to be a single element of T, and there has to be an output. Okay, so let's kind of focus in. It's good to kind of, as you're getting used to higher mathematics, it's good to kind of get used to looking at all of the details in a definition. So there's a lot of details in this definition, so let's focus in on them for a moment. Okay, so there's a to each, right? So this tells me that every input has an output. Okay, and then, so I said that, right? Every input has to have an output. This is the part of, so the definition is what really translates into well-definedness, and this is the part where students get it confused a bit with injectivity, which is a whole nother lecture. Okay, so each input only has one, or a unique output. But this is the same thing as the vertical line test, right? So this is the same thing as the vertical line test way back in your pre-university times, or maybe calculus in university. Right? We only want a single output. This function has to make sense to us. Okay? And the other part that I talked about, right, is I actually want that output to be in T. Right, so if I said that my set of outputs were the positive real numbers, then my output had better be a positive real number. It can't be a negative real number, something like that. Okay, so the output needs to be in T. Okay, and actually, as I've kind of spoken about a little bit, when we return to functions being well-defined, so I'm just going to kind of erase all this now. Right, we will return to this part. Okay, so we'll return to when we discuss that a function must be well-defined. I'm trying to decide, I think, oh, maybe I'll actually put it like this. Okay, so we'll return to all of this when we're going to discuss what it means for function to be well-defined. Okay, great. So precisely one output for each input, and that output has to be in T. And then we have just a little bit of extra terminology here. Right, so this is a little bit of extra terminology. Well, and there's going to be extra terminology, but for the moment. Okay, so there's a name for this S. Okay, so S is going to be called, and maybe actually, okay, I will put it over here. So S is the domain of F. So this is what it's called the domain. Of our function F. And then we have that T is called the codomain. Okay, so T is the codomain of F. Okay, so another way then to write it of what's going on over there is that we could then say that this over here is going to be called the domain, and that over there is going to be called the codomain. Which is going to be slightly different than the range, which we'll get to in a moment. Okay, so we have a function. It starts with an element in S, or for each element in S, I want an output, I want a single output, and it has to be an element of T, and all of that actually kind of boils down to what well-defined this is. The inputs are called the domain, and then the possible outputs are called the codomain. We don't necessarily hit all of them. Okay. Okay, so now we're going to go into images, preimages, and ranges. And we're still assuming, so we still have all the assumptions that we had before, so we're still assuming that S and T were set, right? So our inputs and outputs are set. Right? And then we have a second assumption throughout this, which is going to be that F is going to be a function going from S to T. Okay, so throughout what we're going to talk about now, these are going to be our assumptions. Great. So here we go, our first definition. So we're going to say that, so the image, and this has more than one name, so this is the image. I'm going to draw it suggestively purple, or box it suggestively purple, or another name for it is the range. Okay, this is still of our function F. It's going to be a set, and in particular it's going to be the set of all the elements that are hit, because it's not necessarily true that everything of T is hit. Okay, so this is going to be the set. It's denoted like this. This can get a little confusing sometimes with students. This is actually a set. Remember that this is actually a set. It's not a single element, it's a set. And it's going to be the set of all elements that get hit by F. So I'm going to take the set of all, I'm going to enter in each element of S. So I'm going to range over this, and again, if this notation is confusing to you, you can look at the set notes or watch the set video, okay? And this is going to be a subset of T. Okay, so, and this is precisely, so this is the image. This means defined to be, okay? So its definition is it's a set, and how do I get this set? I take all the elements of S, I apply F to them, and I get the outputs, and that gives me all of it, okay? And so I can kind of write that colloquially here, which I might as well just do, which is that it's the set of all outputs for the function right, the set of all outputs for f, or for my function f. Okay, and the picture then, we start with our picture from before, which I erased. So we start with our domain like this, right? So here's my domain S. And then I have potential values over here, right? I kind of talked about this before, but these are just kind of potential values. So this is like my codomain. Okay, and then I have, right, sitting inside of there is everything that I actually hit, okay? So this is called f of s, and it's called the image, or sometimes we like to call it the range. Mathematicians do this, we come up with more than one name for the same thing. Okay, so then we're just looking at s, and everything, right, f only takes things into here. Okay, so my f only takes things into here, but this is precisely where it takes things to. Okay, so now, we're going to suppose that we have some kind of subset of our codomain. So x is going to be a subset of our codomain T. I don't know if you can tell apart those colors there. So then by definition, so the pre-image of x. Okay, so what is this going to be? So this is again going to be a set, just like it's always good to keep track of what kind of object you're talking about. This is again a set. This is another one that sometimes students confuse. And so the pre-image is going to be, so the set is denoted like this, so I'm going to take, okay, that looks weird. We're used to seeing this and just thinking we're applying it to a single element, but we're looking for all the outputs in some sense of that. But this doesn't really make sense to say all the possibilities for that, because nobody said that this is actually an injective function. So you actually kind of need to look at this as a set. So this is the set of all, but there's like this workaround for that. So this is a set of all elements in S. Right, so we're looking at elements of S, so we can now see that this has to sit inside of S. We can already tell that. So it's a set of all elements, so that f of S is going to actually be an element of this set X. Right? Okay. And so in particular, so this is something to keep track of. So X is a subset of T. This is a subset of S. So we can draw a picture of that. And then, yeah, I'm going to draw the picture and then I'll say the IE. So I have my S down here. And I'm really concerned with, right, so there's some kind of function F that's going to take me over to T. Or into T, right? And last time we were looking at everything that was hit, right? In general, so that was this purple thing. But in fact, actually, this is a no, this doesn't actually have to be a subset of that. So this is, I don't want to draw the purple thing here because they might kind of overlap like that, but not be the whole thing. And that's okay. And so we have our, this kind of x, so this sits inside of t. And what I'm interested in is instead of looking at all of, all of where F hits, I want to go back and I just want to look at what goes into here. Okay, so for a moment I'm going to erase, this. Okay, so that was, I know that F goes from here to here, but I'm only interested in what lands inside of here. Okay, so I'm going to look back here at what actually lands me inside of there. So I'm only looking at the parts. So some parts are going to land out there. I don't care about them. I just want to know what lands inside of X. And our name, right, then for this orange piece here. So this is our F inverse of X, or the pre-image, right, of X. So it's everything that's going to hit that. It's a set that lives inside of S. Okay? So i.e., this is going to be the subset of S. Consisting of all elements of S mapped by F to an element of T. Sorry, to an element of X. Okay, so we have the pre-image, we have the pre-image over here, which is that if I have a subset here, I want to know everything that got mapped by F to it. So my subset, it's a set, but in particular, it's a subset of S. Over here, this is a subset of T, which is all of my outputs if I put in all of S. Okay? So now let's kind of go through some examples. So these are examples of function terminology. So here's example 1. So I have that F is a function that's going to go from, I liked my other blue a little better, but that's okay. So it's a function where my inputs are integers, right? So this is the set of integers. Students always ask why Z. It comes from a German word. We have our outputs have to land inside of R, so that's our codomain. And we have the function, and now this is kind of a typical way to write a function. So I write over here, if I can write it in a general form like this, then I write x and I put a little vertical thing there. So this goes to x squared plus 1. So this is just kind of a typical shorthand, right? So this is shorthand for, you can do this when you have like a nice way to write your function like that, an actual formula. So this is shorthand for saying that f of x equals x squared plus 1. Okay, so in the picture, it's good to at least know in simple examples how the picture lines up with everything else that's inside your head already. So we have our domain Z. And then we have our codomain R. Right, so this is our codomain. And then we want to have, I'm going to put a line here to make sure that this is visually easier for you. Okay, so that's our codomain R. And then if you look at, so if I actually put, so, and this is not actually, it's not actually all of R here, so this should be the integers, just look kind of discrete, like some evenly spaced dots. Right. And then if I went ahead and graphed this function, okay, so what happens if I put in, so if this is, so these are 0, 1, 2, 3, 4, 5, 6, 7, this is -1, -2, -3, -4, and so on. Okay, so if I go